Greetings! Isang pagbati na puno ng kaalaman. To end our discussion on finite element method, since we have already learned how to come up with the element stiffness matrix and the element matrix as a whole, our task is now to assemble the different element matrices that we have obtained in order to form what we call the global matrix, such that we return to the bigger chunk of the figure and apply, or the problem rather, and to apply the appropriate boundary conditions in order to solve problems using the finite element method. Now, let's go straight to the point and how do we assemble the global stiffness matrix. So for example, I have a bar element over here, or system of elements, let's say, that has, for example, 6 nodes, 1, 2, 3, 4, 5, and 6 nodes, right? And let's say that this is a problem wherein this is an axial member, a series of axial members. So 1, 2, 3, 4, 5 elements with 6 nodes, right? That is subjected to an axial load. Therefore, the expected displacement would just be along, right? Along one direction, in this case, along the horizontal, right? The expected size of the global stiffness matrix is a square matrix whose number of rows and number of columns is equal to the number of nodes. So in this case, we have 1, 2, 3, 4, 5, 6 nodes. Therefore, our global stiffness matrix will be a 6 by 6 matrix. Again, that is the size if we have a series of elements which are expected to displace in a single direction only, right? So take, for example, element 2, right? Well, from our previous discussion, for example, I have element 2 over here, and the local node numbers would be local node 1 and local node 2, but globally, in the bigger picture of things, it's labeled as node 2 and node 3. Such that from our previous lecture, if we assemble the element stiffness matrix for element 2, I have whatever that K is. In our case, that's AE over L times 1, -1, and -1, 1. And again, the first column represents, looking back at the global numbers, the first column will represent node 2, while the second column will represent node 3. We can subdivide this into 4, right? And again, we can plot this local matrix in the global matrix by, for example, I can look at the subregion 2, 2, meaning what is at, let's say, column 2 and row number 2, right? It's 1. Therefore, I'll also place it here at row number 2 and column number 2. So it's K2 over here. Then, for example, I have column 2 and row 3. That's -1. So I just factor in K2 over here. So that's negative K2. So I'll place it in the global matrix in column 2, row 3 as well. So that's negative K2, and so forth and so on. Let's try to look at the next element. Let's say element 3 with global nodal numbers 3 and 4. So this is the element stiffness matrix. Again, this would be labeled as column 3 over here. This would be labeled as column 4 for node 4. This would be labeled as node 3, and this would be labeled as node 4. Again, 3 and 4 are the global node numbers for element 3, such that, again, I will place column 3 and row 3, so this one over here, in column 3 and row 3 of the global matrix. So this is K3 over here. But in the previous slide, there was a value for row 3, column 3 as well. Therefore, I just add the two values. So meaning it's just a matter of imposing superposition, of a principle of superposition, if one element coincides, or the node of one element coincides with the node of another element. Hence, we can now form what we call your global stiffness matrix. Let's try to look at this example. This is example 11.1, and I believe this was the example that we solved previously. So please grab a copy of our solution from the previous element stiffness matrix, and our goal now is to assemble the global matrix of the system. Right? So please grab a copy of this problem while I shift to my solving board. Okay, so this is example 11.1. Recall, from example 10.1, we have obtained the following element stiffness matrices for steel member and for the aluminum element over here. And please take note of the node numbers. This is 3, this is 2, and this is 1. So again, what we do is from our element stiffness matrices, I can just divide this, right? Like so, right? And similar to the element, for the aluminum element, I can subdivide it as such, right? And I can say that this will represent, as we have mentioned, this is the steel element. So this is node 3, this is node 2, this is node 3, and this is node 2, right? For the aluminum element, this is node 2, this is node 1, as we have obtained previously, node 2 and node 1, right? Such that I can now assemble my global matrix. I have 3 nodes, and again, the expected displacement is just along one direction, okay? So one direction only, therefore, I should have a square matrix that is 3 by 3, correct? Because I have 3 nodes, therefore, right? I can have, this is now the form of my global stiffness matrix, okay? So just as a recall, okay, I can say that I have a 3 by 3 matrix and just label it as, again, node 1, 2, 3, node 1, 2, 3. Okay? So again, I just fill up. Okay? So if you want to know how this were obtained, okay? So the global stiffness matrix would be a 3 by 3 matrix. Okay? 3 by 3 over here. So again, what is placed in column 1 and row 1 would be, where is that? Going to your element stiffness matrix. So I'll just, again, plug in one by one. I'll just write here 1, 2, 3, 1, 2, 3. Okay? So again, what is contained in row 1, column 1, go back to your element stiffness matrix. Row 1, column 1 is this one. Right? Row 1, okay? Column 1, labeled, again, row and column. Right? Such that I have 175 times 10 cubed. Right? Next, what is row 1, column 2? Right? So row 2, column 1. Okay? So row 2, this is row 2, column 1. Okay? So I have negative 175 times 10 cubed. Right? Next, how about row 3, column 1? So row 3, column 1, I don't have any combination of row 3, column 1 in the figure. Okay? So I don't have any combination of row 3 and 1, okay, in my element matrix. So this is 0. Next, how about for row 1 rather, column 2. So row 1, okay, again, row 1 and column 2. Okay, so this is row 1, column 2. Okay, this is negative 175 times 10 cubed. Okay? Next is, what is row 2, column 2? Okay? So row 2, column 2, I have row 2, column 2 over here. Actually, I have 2 values. Row 2, column 2. Okay? And also here, I have row 2, column 2. So I just, oops, that's not row 2, column 2. This is row 2, column 2 rather. Okay? So I have 2 values, okay, in row 2, column 2. So I just add those 2, and my answer would be 535 times 10 cubed. Next, what is row 3, column 2? So row 3, column 2 is, where is row 3, column 2? Here, this is row 3, column 2. Right? So this should be negative 360 times 10 cubed. Right? And finally, what is left of us is for column 3. So I have row 1, column 3. So row 1, column 3, I don't have any combination for row 1, column 3. So that's 0. Next, how about row 2, column 3? I have row 2, column 3. So this is row 2, column 3. Right? So that's negative 360 times 10 cubed. Next, finally, I have row 3, column 3. So row 3, column 3, it's this one. Right? So this is 360 times 10 cubed. Right? So this is now my global, right, stiffness matrix. Right? Oops. Well, we'll just highlight as so. Right? So are there questions? Okay. Now, again, we just go back to our example, right? So, and double check if our answers are correct, right? This is, I think, in kilonewton per millimeter, if I'm not mistaken. Yeah, it's in kilonewton per millimeter. But our solved example, I solved it as Newton per millimeter. Okay. Next, let's look at the next example. What if I'm being asked to assemble the global matrix? However, my problem involves elements which have inclined members, right? So in this case, since our global axis would be x and y, right, please expect in this case that displacements can occur along x and along y, not only in the y direction. Therefore, for problems such as this, wherein we expect our problems to have displacements along x and y, right? The size of the matrix would be, right? The size of the matrix would be a square. It's still a square matrix, but the size now is, right, the number of rows is still equal to the number of columns, but, right, it would be equal to the number of nodes times 2. Why times 2? Because previously, right, it's only a single direction. However, in this type of problem, it's double the 2 directions, meaning x and y. That's why we have times 2. So we need to account for the x direction and the y direction. Okay? So in this problem, as you can see, right, we have a truss with 3 nodes. Therefore, expect our global stiffness matrix to have 3 times 2. Therefore, 6 by 6 stiffness matrix. So at this point, kindly grab a copy of this problem and recall our solution for the element stiffness matrices while I shift to my solving pad. Okay, so this is example 11.3. Recall from example 10.2 that these are our answers for the element stiffness matrices. Okay? Now remember that, again, what we can do is we just subdivide, okay, our matrix, okay, such that per element I have 2 nodes, so I just divide. Okay? This is one division and another division. And for element 1, remember that we have node 1 and node 3 and node 1 and node 3. Now, please take note that for each column and for each row, it's being represented by 2 numbers because I'm considering x and y, x and y. Okay? So same is true with this xy, xy. Okay? So for the second element, okay, again, I just divided into 2. Okay? Looking at the global numbers, element 2 was node 2 and node 3, and this is node 2 and node 3. Okay? Therefore, for per subgroup or per column and row, I have 4 numbers which I can place in my global stiffness matrix. Right? So in my global stiffness matrix, I'll just minimize a little bit. Okay? So in my global stiffness matrix over here, I should expect a 6 by 6 matrix. So again, this is node 1, node 2, node 3. This is node 1, node 2, node 3. But again, per node, we have 2 values because we are considering the x and the y direction. Okay? So instead of having a 3 by 3 matrix, I have a 6 by 6 matrix. Okay? So first things first, okay? We can just substitute. We look at row 1, right? Column 1 over here. Right? So row 1, column, again, row 1, column 1. So going back, where can we see row 1, column 1 in our element stiffness matrices? So this is row 1, column 1. Right? So I'll just copy 0, 0, and 0, 1. Right? This is 0, 0, 0, 1. So that's for the X and Y. Next, how about row 1 and column 2? Row 1, column 2, we don't have that combination. So that's just 0, 0, 0, 0. How about row 1, column 3? So row 1, column 3 is this one, row 1, column 3. So it's this, row 1, column 3. Right? So it's 0, 0, 0, and negative 1. Next, how about for row 2, right? Row 2, column 1. So row 2, column 1, we don't have any row 2, column 1. So that's 0, 0, 0, 0. How about row 2, column 2? So row 2, column 2 is found in element 2. This is row 2, column 2. But is it okay? So that my element stiffness matrix, before I proceed, so that if I factor out AE over L, please take note that in element 2, there's 1 over square root of 2 that I need to multiply in all my terms, so that a common thing for element 1 and element 2 is AE all over L. So if I multiply everything in element 2 by 1 over square root of 2, I should be left with 1 over square root of, in this case, 1 over square root of 2 over 2. And if I rationalize, that's square root of 2 over 4. Correct? Okay. So I just subdistribute and multiply square root of 2 back inside. So element 2, 2 and 2, row 2, column 2 will be square root of 2 over 4. Right? So everything will be square root of 2 over 4. Right? Square root of 2 over 4 and also square root of 2 over 4. Okay, next. Row 2, column 3. Where is that one? Row 2, column 3. Right? This is row 2, column 3 over here. Again, I just multiply by 1 over square root of 2. Right? Such that they're all negative. Right? So it's the same as this one, but I just need to place a negative value. Right? Negative and negative. Next, how about let's substitute or let's fill in row 3, column 1. So row 3, column 1 is row 3, column 1. So this one, right? So that's 0, 0, 0, negative 1. Then row 3, column 2. Where is row 3, column 2? Row 3. This is row 3, column 2. So it's this one over here. So row 3, column 2, it has a negative. So everything multiplied by 1 over square root of 2, right? So it's this one. Then, lastly is row 3, column 3. So again, if I look at row 3, column 3, I have row 3, column 3 over here multiplied by 1 over square root of 2. And similarly, I have row 3, column 3 over here. So I superimpose and add those two, right? Such that my final answer here would be square root of 2 all over 4. This is square root of 2 all over 4. This is square root of 2 all over 4. Since all of these three are 0, then I have here 1 plus square root of 2 over 4. So this is now our global stiffness matrix. Don't forget to multiply it by AE over L. Okay? So kindly absorb first. Is that clear? I hope that's clear. And we'll try to shift to our PowerPoint slide just to double check. Okay, so this is the answers as projected in the slide. So we got the same answers as what we have solved. Okay? So that is how to assemble the global stiffness matrix. Now that we have the global stiffness matrix, we can now apply our boundary conditions in order for us to solve the problem. And in our case, the boundary conditions will come from our general equation that we have been dealing with actually loaded members. F, the force, is equal to K, where K is the stiffness, the global stiffness matrix, and D is the displacement vector. And again, our goal is to look at Possibly support reactions wherein we know the behavior of the displacements, wherein a direction is prohibited, or let's say we have prescribed displacements, we'll add them to our known values of displacements. Or we could also say applied forces in our nodes. We can substitute those values in our F matrix, right? So let's try to solve an example. Again, this is the same example, example 11.4. Right? We'll just continue our previous examples that we have solved. We are being asked to determine the displacement, right? Take note, displacement of nodes 2 and 3, knowing that F2 is 1.5 kilonewtons and F3 is 2 kilonewtons. So in this problem, the boundary conditions, which are the known values, would be F2 and F3, and also additional boundary condition is a displacement of node 1. Since node 1 is fixed, right, is a fixed end, we know that the displacement should be equal to 0. Right? Since that's a fixed end that cannot displace. So again, please grab a copy of this problem while I shift to our solving pad. Right? So this is example 11.4. Okay. So F is equal to KD such that, again, I have 3 forces. Therefore, I have F1, F2, and F3. I have 3 nodes. And I have my global stiffness matrix K. And again, D is just the displacements of each node. Again, in a single direction only. Therefore, that's U1, U2, and U3. Correct? Okay. Such that I now have F1, which is unknown. That's at the fixed end. F2 and F3 are known. That's 1,500 newtons and 2,000 newtons for F3. Then my global stiffness matrix is shown here. We have solved this in the previous example, so I just copied the global stiffness matrix. Then U1, U2, and U3, again, a boundary condition. We know that U1 should be equal to 0 because U1 is a fixed end, so it doesn't displace. Then unknown U2 and U3 displacement. Right? Now, we have 3 sets of equations with 3 unknowns, F1, U2, and U3. However, to make our lives easier, what I can do is I can reduce my system of equations by only considering this portion, the highlighted portions. And again, since U1 is 0, right, this first column I know will represent the coefficient, right? And if I multiply everything by 0, this cancels out, right? This portion over here, this cancels out because, again, U1 is just equal to 0, so everything cancels out. Therefore, I can consider this portion only, U2 and U3. Therefore, my reduced system of equations, in this case, would be this matrix over here. The portions which are not highlighted will not be affected primarily because U1 is equal to 0. Right? So it will not affect my solution. Okay? So if I solve this reduced system of equation, I should get, you can use any available application for you. I think the easiest would be Excel spreadsheet. Right? So perform this matrix operation. U2 is equal to 0.02 millimeters and U3 is equal to 0.026 millimeters. Right? There. And plugging into our matrix, going back to our original matrix over here. Right? So going back to our original matrix, we can also say that F1 is equal to negative 3,500 newtons or 3,500 newtons to the left. Okay? And you can perform equilibrium to check that that is indeed the final answer. Okay? So please absorb first. Are there any questions? Okay. So looking at our final answer, apologies, there's a mistake here. This should be 0.02 millimeters, and this is 0.026 millimeters, not meters, right? So to double check our finite element method analysis, okay, you can perform your mechanics of deformable bodies approach, delta equals PL over AE to check the deformation. But then again, that's deformation, so you need to adjust in order to get the displacements for node 3. Okay? So those are our final answers. Next, let's try to look at this final example. Determine the displacement of node 1, of node 3 rather, and the reactions at 1 and 2, which are both pin connected, if there is a 10 kilonewton horizontal force acting at node 3, strictly using FEM, knowing that the cross-sectional area of the member is 1,000 square millimeters, the modulus of elasticity is 200 gigapascals, and L over here is 1 meter. Okay? So again, please grab a copy of the problem as well as a copy of our global stiffness matrix that we have previously solved while I shift to my solving pad. Okay, so let's continue solving. Okay, so again, our governing equation for an actually loaded system is F is equal to KD, where K is my global stiffness matrix, and F would be the forces applied at the nodes, and D would be the displacement of the nodes. Okay? So again, since we have a system, a truss, having inclined members, as we have shown, our global matrix would be, we have 3 nodes, so times 2. So we have a 6 by 6 global matrix shown in red over here. Right? And if we plug in F is equal to KD, right? I know that I have 3 nodes, therefore I have F1x, F1y, F2x, F2y, F3x, and F3y equal to the global stiffness matrix K multiplied by the displacement matrix U1x, U1y, U2x, U2y, U3x, and U3y. Okay, therefore, just plugging in, well, F1x and F1x, F1y, they are known. F2x, it's unknown. F2y, that's unknown. F3x, I actually know F3x. It's said in the problem that the force applied at node 3 is a 10 kilonewton horizontal force. Therefore, I have 10,000 newtons. And F3y, since it's purely horizontal, is 0. Times the global stiffness matrix. Again, this is A over here as 1,000 square millimeters. E is 200 gigapascals, and L is 1,000 millimeters. And I just copied the global stiffness matrix that we have solved previously. Then, plug in my displacement matrix. I know that 1 and 2 are support reactions. They are pin reactions. Therefore, they are not allowed to displace. They're not allowed to displace along any direction. Therefore, U1x, I can say that U1x is equal to 0 because it's not allowed to displace. U1y is also not allowed to displace. Similarly, U2x and U2y, both 0, they cannot displace. They are pin connections. But node 3 is free to displace, so it's an unknown. I have U3x and U3y. Are we clear? Now that we have zeros over here, I can solve this system of equations, but I can reduce my system of equations so that I can remove some parts of the matrix because they will not be affected since these portions over here are all equal to 0. So that represents column 1, column 2, column 3, and column 4. Correct? And again, I can also remove row 1, row 2, row 3, and row 4 without affecting my reduced system of equations. So I am only taking row, the 5th row, this one, and the 6th row with U3x and U3y. Okay, so let me just highlight again. Okay, so this is now my system of equations. Well, it's up to you. You can solve them as one. It's up to your discretion on how to easily solve this matrix operation. And you can use your Excel spreadsheet if you don't want to reduce your system of equations. That's okay. But I think it would be easier because there are a lot of zeros. Once I perform this reduced system of equations, I should get U3x equals 0.191 millimeters and U3y to be equal to negative 0.05 millimeters. So this would now be our final answers for U3x and U3y. And similarly, considering the parts of the matrix which I didn't consider earlier, again, in this case, I'll now use this red highlighted portions. Again, they will not, reducing the system or taking out parts of the matrix will not affect, please be very careful, will not affect our solution in this case because I have zero values, so they will just cancel out. So don't just, in your succeeding problems, don't just take out any part of the matrix. Please be careful. So review your matrix operation so that you know how to, or which parts of the matrix can be removed. Then I'll take the red portion. So it's just this portion over here. Because again, column 1, 2, 3, and 4 are all 0, so they cancel out. And I have U3x and U3y only. Okay? So in matrix form, it's this one. I already know U3x and U3y. Therefore, I now know that I have my final answers as I perform my matrix operation. I should get F1x to be equal to 0, F1y as 10,000 newtons, F2x as negative 10,000 newtons, and F2y as negative 10,000 newtons. So this would now be our final answer for F1, F2, and F2. X and Y components. So that is how you solve example 11.4. So you can check using equilibrium, you can check using statics that these indeed are the support reactions. So please absorb the problem. And I hope you understood how to solve and how to assemble the global stiffness matrices, and apply the boundary condition to solve problems. So that ends our lecture on finite element method. In our 3-part lecture series, we have learned how to assemble the element matrix, then the global matrix, and finally to assemble by applying the boundary conditions rather in order to solve problems involving one-dimensional elements. I hope you learned a lot. Thank you very much.